Hello, my name is Zachary Chenoweth, and this is my presentation of Lab 2, Task 3, Wall Following in the Corridor Map. For this task, we have to have our ePuck robot wall follow and traverse through this corridor, making only left or right turns depending on which controller we are using. For this controller that we have here, this is the left turn controller. We have our initializations for the robot, our constants, which sets the maximum minimum velocity, proportional gains, the desired distances from the walls, and then the length of time we want our simulation to run. We have our F saturation function, which basically caps the velocities so it does not exceed the minimum or maximum velocities when we calculate it. This function here is responsible for the left turns. So basically it'll loop through, turn 90 degrees, and then continue forward. This function is for the robot when it hits a wall and it cannot make a left turn, it'll turn 180 degrees backwards and then continue forward. So it'll turn around and then continue in the new direction. Our forward velocities function uses PID to calculate the proportional velocity that we want to set our wheels to. It does this by calculating the error, which is the desired distance minus the current distance, and then multiplying it by the proportional gain and then saturating that value. Then we convert it into radians per second and then call these two functions for each wheel so we can set the velocities of the wheels depending on the distance from the left and right walls. Here's the function for the left wheel, and it's similar to the forward function, except with some changes. We calculate an error, and we set our velocities depending on if the error is negative or if we're reading our reading for the front distance sensor is 7. Then we want to set the velocity to the calculated value we calculated in forward velocity. Otherwise, if the error is positive, then we want to go ahead and calculate what we want to set the wheel to in order to keep it away from the two walls. And then we set that velocity to, we set that motor to whatever that velocity we calculated is. The right wheel does the same thing as the left wheel, except for the right wheel. So we look at the left distance sensor, the opposite wall to the wheel, calculate the error, and then set our velocities. Here in the main loop, we check how much time has passed in the simulation. We read our current distance sensors and then print them with 4 decimal precision. Then we say if time is passed, we want to go ahead and move forward as long as the front distance sensor is not up against, like it's not reading a wall in front of it within 7 inches. And then if it is up against a wall, then we want to either turn around or turn left, depending on if a left turn is possible. And then once the time is complete, we want to stop our robot and then break from the loop, which ends the program. So let's go ahead and see this one run. So as we can see, the robot starts out and it tries to keep away from the wall within some margin of error. So it's going to kind of zigzag back and forth. It's going to hit this corner and realize that it can't make a left turn, so it's going to turn 180 degrees and go backwards. Again, it's following this path, so it's readjusting whether it's following this wall or this wall. It gets to this wall and then turns left and continues on the corridor, and now it'll continue doing that, making left turns until the program ends. As you can see, the robot will keep adjusting and following the walls, and it's either going to choose to follow this wall or this wall, depending on which one it's closer to, and it wants to keep a distance of about 7 inches away from the wall, so that's why it keeps moving back and forth in a zigzag motion. Okay. So now let's go ahead and see the right turn corridor controller. So this controller is basically exactly the same as the left controller. You have your initializations, your constants, your saturation function. One of the differences is that this function makes it turn right rather than left. So we turn 90 degrees to the right rather than turning to the left. The turnaround function does the same thing as the previous controller. And then we have our forward, left wheel, right wheel, which is exactly the same as the left turns controller. And then we have our while loop. Again, most of this is basically the same as the left controller. The only differences here are that we're calling our turn right function, and we're also looking at if there is a wall on the right side rather than the left side to see if a right turn is possible or not. Then we set our velocity to 0 and break from the loop once the time has passed. Let's go ahead and see it run. Okay. So as you can see, it does the same thing. It's trying to follow the wall that it's closest to, and then it's adjusting its angle. It's going to come up on this wall, and then it sees that it can make a right turn, so it turns right. And then follows the corridor again, making adjustments and following whatever wall it's closest to. And turns right. And then this will continue on until the robot completes corridors and the time runs out. Up in this corner, we can see the camera that the robot is using, so you can see what the robot sees as it's traversing through the corridor. Here we have our current distance sensor reading. We have the front distance sensor, the left, the right, and then the current time of the simulation. And this will keep going until about 90 seconds have passed, and we'll keep continuing in a loop. So that's lab 2, task 3, motion in the corridor using wall following. Once again, this is Zachary Chenoweth, and have a wonderful day.